Bueno, buenas tardes a todos. Bienvenidos al seminario del día de hoy. Eh, el doctor Víctor Mayta es un científico investigador especializado en ciencias atmosféricas y oceánicas. Cuenta con maestría y doctorado en la Universidad de Sao Paulo, Brasil. Actualmente trabaja como Research Scientist en el Departamento de Ciencias Atmosféricas y Oceánicas en la Universidad de Wisconsin-Madison. Su enfoque principal está en la dinámica atmosférica a gran escala, con especial atención a la meteorología tropical. Ha investigado temas como la oscilación de Madden-Julian, las ondas de Kelvin, la variabilidad interanual en los océanos Pacífico y Atlántico y la paleoclimatología. Pues Víctor, bienvenido y gracias.
Ok, gracias por la presentación. Primero, muchas gracias por la invitación. Es para mí todo un placer presentar hoy en el grupo. Como me presentaste, yo soy Víctor Maita de la Universidad de Wisconsin y voy a pedir unas disculpas aquí porque voy a presentar en inglés. No, no es porque me quiera dar el gringo, no, sino que yo aprendí meteorología en portugués y en inglés y muchas de las cosas no sé cómo decirlo en español. Bueno, vamos a comenzar entonces. Eh, okay, the topic of my presentation today is the Stirring Tropics. I will talk about a little bit about moisture modes and moisture vortex instability. And I will start with showing this animation, which is basically Brennan's temperature. It's commonly used as a proxy of convection, and I use it quite a lot in my talks. Um, as you can see, you probably see that over the tropics, you will see, oh yeah, the convective organization is pretty disorganized, it is chaotic, but this one is chaotic because tropic contains a diverse water system with a wide variety of spatial and temporal time scales. I show it in this space-time spectral. So, so the reason why the tropic is a super disorganization is because all these disturbances like MGO, Kelvin, and all disturbances are acting at the same time. And this is why you will see like all this is the convective organization is a little bit chaotic. But if you take, for instance, the information of the Madden-Julian oscillation and plot together here in this animation, you will see, for instance, that large portion of the convective system is in fact organized by this Madden-Julian oscillation, which is propagating eastward and impacted precipitation not just over the tropics, but also impacts the higher latitude by the so-called like tropical and subtropical teleconnections. In the same direction, propagated Kelvin waves here show it in as a red circles, and also impacts pretty well in the precipitation over the tropics. The green curves here represent the easterly waves. Maybe in Mexico is also a system that impacts precipitation. On all the systems that I described previously can be divided, can be separated into regimes. I call them two regimes. And one is the called unbalanced regime, and the other one is the balanced regime. And a perfect example, for instance, for this unbalanced regime represent the westward inertial gravity waves, so the wicks. In this case, for instance, I'm showing these wicks over the tropical South America. And the feature that characterizes these disturbances is that, in fact, is a short time scale. These have a very fast propagation. For instance, over the tropics, this one propagated about 35 meters per second. Another important point is that temperature play an important role in the thermodynamics and dynamics of this kind of disturbances. In the opposite, we have the balanced regime, and a perfect example for these disturbances represent the equatorial Rossby waves. Again, I'm showing over tropical South America that in fact these Rossby waves also impact precipitation over Mexico. So what characterizes this balanced regime? First of all, it has a long time scales, at least compared to this weak waves over the tropics of South America. The other one is the slow propagation. For instance, this one propagates at about 5 meters per second. And the other one is that moisture plays a central role in the thermodynamics and dynamics of these disturbances. As you may notice, I highlighted two important features in this balance regime. First of all, slow propagation, and second one, moisture play an important role in the thermodynamic of these disturbances. So why I mentioned that? Because convective coupled waves, so the waves that I mentioned previously, I always view it as an extension of the dry waves with a reduced equivalent depth to represent moist convection. So this is the Matsuno theory. In the Matsuno theory, these waves exist. But in the, so many studies try to represent these moist waves as an extension of this dry theory. But the question is that the theory can explain the all observed future, at least for the slow propagation disturbances. And the question is maybe not. And one example, for instance, represents the Madden-Julian oscillation. In the theory, doesn't exist any dispersion curve that explain the Madden-Julian oscillation. The other one represents the TD-like disturbances or the hysteresis waves. Again, we don't have any dispersion curves that represent, for instance, this hysteresis wave activity over the tropics. In fact, this theory doesn't explain that we observe it in the tropics, at least for the waves that propagate slowly. Okay, let's go to the tropics. Why the tropics are so excited, why the tropics are so interesting. So we can say there are two main features that characterize the tropics. The first of all is the weak temperature gradient. As observed here in this temperature map, and this is for the tropical domain, you will see that temperature, at least at the lower troposphere, is pretty homogeneous. You will see any changes either in time and either in space. So compared, for instance, with mid-latitudes. The other feature is the large moisture fluctuation, which was observed over the tropics, that in fact drives the wave activity and the convection over the tropical domain. This gives us one important consequence. In this case, is the existence of the moisture modes. If you're not familiar with moisture modes, we can easily define as a type of tropical motion where the water vapor play a central role in the dynamics and thermodynamics of these disturbances. As I mentioned previously, these disturbances doesn't exist in the dry theory. Okay, let's go to the main scientific question we try to answer in this talk. First of all, we try to answer if this moisture mode exists or not. The second question is if the moisture mode exists, where they are more common. And the third question is what process control, of course, if the moisture mode exists, the propagation and the growth of these disturbances. And finally, we try to answer what is the role of these moisture modes in the general circulation. To answer this question, we basically used a brightness temperature. The same I show it in the animation, and we will use aerofiber analysis data to describe the circulation and the thermodynamics associated to these disturbances. Okay, so how we can know if this disturbances is or not a moisture mode? In a previous study, ACME 2021, Mayta 2022, proposed 3 criteria to identify these moisture modes. So what exactly says each criteria? The first criteria basically says that moisture anomalies must exhibit a high coherence with precipitation anomalies. So basically, a strong correlation between total column water vapor and precipitation should exist to say that our disturbances is in fact a moisture mode. The second criteria says that the wave should be in WTG balance. So as we showed previously, WTG should be true to say if our disturbance is not our moisture mode. And the third criteria basically said that thermodynamic variation in the wave must be dominated by moisture. So in other waves, the moisture fluctuation in the wave should be much larger to temperature fluctuation. And the fourth criteria is we can also know if our disturbance is in non-moisture mode by using this N mode parameter that basically measure the contribution of temperature and moisture in the thermodynamics of the wave. If this N mode parameter is much less than 1, we can say, in fact, our disturbance is a moisture mode. A more strict definition of this N mode can be defined by using the, for instance, the phase speed propagation of the wave, Cp. This tau represents the temperature variation of your wave. This C is the phase propagation of the gravity wave, and this tau C represents the convective moisture adjustment time scale. This N mode can be plotted as a wave number frequency. I show it in this figure. In this figure, the contour represents the spectrum of the waves. For instance, here, the spectrum of Kelvin waves, MGO, Rossby, TD, and Wicks. And also, N mode is plotted here in shading. So what exactly the shading corresponds to? Everything that's in blue in this diagram means moisture mode. The region in white represents the mixed system, or where temperature and moisture play the same role. And the yellow one means the gravity waves, or where temperature fluctuation basically is driving the wave thermodynamics and dynamics of the wave. As you can see here, you will see like a large portion of the TD or easterly waves and Rossby waves are in the blue region. I show it here, which means these disturbances are a moisture mode in the whole tropical domain. The other disturbances that can be considered a moisture mode is the Madden-Julian oscillation. But the Madden-Julian oscillation sometimes behave as a moisture mode. So you can see like some portion of this spectrum associated with the MGO fall into the blue region, but sometimes this behaves as a Kelvin wave, which means it's a mixed system, especially when the wave is propagating outside the warm pool regions. So based on all criteria, and including this N mode, we can say that our easterly waves and Rossby waves are the only moisture modes in the whole tropical region. Remember that MGO is a special case. Okay, so by using our criteria, we demonstrated, in fact, that easterly waves and Rossby waves are the only waves that can be considered moisture modes in the whole tropical domain. So now the question is where these disturbances are most common. To answer this question here in this figure, contours are plotted total column water vapor or moisture, and the shading here represents the wave activity. The first panel represents for the easterly waves, and the second panel is for the quadruple Rossby wave. As you can see here, for instance, if you focus here in the Atlantic region, you will see that the maximum wave activity represented by shading here, in fact, is collocated over the region of maximum gradient. Know where the maximum moisture is collocated. I show it here. The same you can see here over the Western Pacific. So the maximum wave activity is not located here, right? The maximum wave activity is located where the moisture gradient is located. So the same happened to the equatorial Rossby wave. So moisture mode occurs over the region of a strong horizontal moisture gradient. Okay, so first question was if moisture mode exists. We say yes, moisture mode exists. And where this moisture are more common, this moisture mode exists where the maximum horizontal gradient is observed, not where the total column water vapor is maximum. Okay, the third question was which process control the evolution of this moisture mode? To answer this question, so which process control the growth and propagation of this wave, we can use this column MC budget. If you're not familiar with this MC budget, this term, for instance, represents the horizontal advection. This is the vertical advection of moisture. radiated heating is represented here by QR. And this one we can call the fluxes. This basically tell us how moisture is evolving into the system. Okay, let's start with the terms that contribute with the propagation of the wave. This is for the easterly waves, TD type wave disturbances. And here, each bar represents how much each mechanism contribute with a whisper propagating of our disturbance. As you can see here, there are many terms because I decomposed the horizontal and vertical advection, but we can say that just two terms are basically responsible for the westward propagation of the wave. Remember that easterly wave propagates eastward, Rossby wave actually propagate in the same direction. So we can say that our disturbances propagate westward because basically these two terms, horizontal moisture advection, specifically by these terms. In this case, this is the advection of moisture by the main flow, or we can say that trade winds is propagating the wave in that direction, which makes sense, right? Okay, horizontal advection responsible for the westward propagation of our moisture modes. Now the question is, which terms are responsible for the wave growth? So which term contribute with the amplification of the wave or the decaying of the wave? Again, we are using the same approach, the MSc budget, but now each term represent how much each term contribute with the growth when we have positive values, or decay when we have negative values. Again, as mentioned previously, horizontal advection and vertical advection were decomposed into the different terms, but I basically highlighted the most important terms. Okay, I will start, for instance, by this term, the radiated heating. So many previous studies demonstrated, for instance, that this term, radiated heating, play an important role in the amplification of the wave. So you can see that during the wave evolution, this term basically contribute with the amplification of the wave. In the opposite, you have this term, the vertical advection of moisture. This term is contributing with a decaying of the wave during the whole evolution of the wave. I completely forgotten, but this one represents the wave evolution, where this red one represents the peak of convection over the domain where you are analyzing the wave. So this basically these days previous to the maximum convection in your baseline or your region you are analyzing, and this one is days after the peak of convection. Okay, so these two terms, as you can see, are super large, but these two terms, as you can see, basically showing the same magnitude, which means these two terms are balanced during the wave evolution. So if you do this calculation, you will see this will be almost zero, which means that really explain the wave evolution, show it by the tendency of moisture, is in fact explained by the horizontal moisture advection, specifically by this one. This is the advection of mean moisture by the trade or by the meridional winds. Okay, you can say, oh, Victor, that is so complicated. You decomposed all the budget terms. Please simplify that. Okay, let's do that. This is the budget equation, but this is the simplified one. This is the horizontal advection. This is the column processes. So all the terms are simplifying these column processes because we basically say that horizontal advection explain the moisture evolution in the wave. So let's show here. So for instance, here is the wave evolution of the easterly waves, where the peak of convection is represented here. And here are represented, the dashed line represent basically the moisture tendency. So how basically explain how the moisture evolved into the system. And the green line represent the horizontal advection. so which is perfectly perfectly shaped in the same evolve at the same atmosphere evolve into the system. And the other processes, we call it column processes, are basically zero, which means all the processes are balanced during the wave evolution. Just this term, the horizontal advection, explain how moisture evolve into the system. So the question now is if the same mechanisms can see in the whole tropical domain. If you go to the Atlantic region, you will see, for instance, these two terms are responsible for the propagation, and this term are responsible for the growth of the wave. If you go to the Eastern Pacific, you will see actually the same terms contributing with the growth and decay of the wave. If you go to the Western Pacific, you will see the same. So the trade winds propagating the wave, and this term responsible for the growth of the wave, and the other one contributing with the decay of the wave. If you go to the Indian Ocean, you will see the same. In conclusion, we can say that moisture modes, in fact, are driven by the same mechanism across all basins. Okay, now the question is, what are the moisture modes are doing? What is the role in the main circulation? So, so in the previous, we basically see that this term always contribute with amplification of the wave. So it means that this term, the meridional winds and moisture, should be in phase during the wave evolution. This can be easily demonstrated by calculating the coherence between these two terms. This is the meridional wind, and this is the moisture. And this is calculated for the southern hemisphere and calculated by the northern hemisphere. As you expected, the maximum coherence between these two terms are observed in the Rowley domain, in the TD-like domain, or easterly wave domain. The same happened in the northern hemisphere. The maximum coherence is observed in the Rossby and the easterly wave domain. So what these terms are doing, basically in the southern hemisphere, exists moisture transport toward the higher latitudes. In the northern hemisphere are doing the same. This term or these disturbances are transporting moisture from the tropics through the higher latitudes. Maybe, and this is not an easy way to see, but we can show the same impact in maps, right? We can plot, for instance, the contours here represent the total column water vapor, and the shaded again represent the wave activity or easterly waves across the all tropical domain. And the arrow here means the eddy moisture fluxes. What we said? Basically, we said where the wave is super active, they basically transported moisture, for instance, from the tropics through the higher latitudes. The same happened here in the Eastern Pacific. So when the wave is active, they basically transported moisture from the tropics through the higher latitudes. In the Southern Hemisphere, the same happened. Here, for instance, tropical cyclone activity or easterly waves are super active, but in this case, again, is transporting moisture from the tropical domain to the higher latitudes. This is, in fact, the main role of these moisture modes, well, in the main circulation. So we can also show this by using this schematic figure. In this case, the ITCC and the Hadley circulation is shown by this overturning circulation. I show it here in this schematic figure. Of course, you will have like more moisture and more precipitation in the ascending branch of the ITCC, and of course, less or dry regions where you have the descending branch of the Hadley there, right? So this one, for instance, can represent 25 north, and this one could be the equator one. Okay, so if you have more moisture here and less moisture here, of course, should exist a moisture gradient. So based in our results, our hypothesis is that this Hadley sail always want to steepen the moisture gradient. What exactly means that? The Hadley sail have the equatorial component, right? In this case, always the Hadley sail is trying to advect dry air from this region to this region to maintain this moisture gradient. But in the opposite, we have this, this eddy, unstable eddies, which is a result of our moisture modes. So as we saw previously, these eddy terms are advected moisture from this region to this region, right? It's trying to keep O2 at the same point, trying to maintain the steady state. So this is in fact the main role of these moisture modes that I described previously. Okay, just to conclude and to put in context, because could be a little bit confused. You will say, "Oh, Victor, what is moisture mode? What is the role in the general circulation?" So let's do an analogous analysis comparative baroclinic waves. Of course, if you studied atmospheric science, you studied mid-latitudes, right? This is tropical cyclones, and we really know that the cause instability of these extratropical cyclones is because the temperature gradient. So we can say these extratropical cyclones exist because the temperature gradient. But the same we can say of our moisture mode. Our moisture mode, as showed previously, exists over this domain. And of course, this moisture mode exists because of moisture gradients. The same to the baroclinic waves, right? So what is the role of this baroclinic wave? We know that this baroclinic wave is a tropical cyclones, polar flux, moisture, and temperature, right? For instance, these extratropical cyclones bring warm temperature from this region to the pole and bring cold and dry air to this region, right? And dictates to day-to-day variability in the mid-latitudes. So the same happened with these moisture modes. But these moisture modes, in this case, are exporting moisture from the tropics through the high latitudes in the both hemispheres. And this is perhaps the main role of these moisture modes. We know also that this baroclinic waves weakens the jet stream, right? When you have strong tropical cyclone, of course, you will weaken these jet streams. The same happened with the moisture mode in this case, but this moisture mode weakened the Hadley circulation as showed previously in the schematic figure. Okay, let's answer our question that I stated at the beginning of my talk. Our first question was, moisture mode exists or not, right? The answer is yes, moisture mode exists. And we have two moisture modes, easterly waves. And equatorial Rossby waves are a disturbance that satisfies the all condition to be considered moisture modes. Where these disturbances are common, I show it pretty easy. We're showing contour and showing wave activity that moisture mode exists over the region of a strong horizontal moisture gradient, nowhere moisture is higher. The third question was what processes control the growth and propagation of this moisture mode? Hopefully, I convinced you that moisture mode were controlled by the horizontal moisture advection. The final question was, what are the moisture modes are doing? What is the role of these moisture modes? And we can say, as the title of my topic, basically these moisture modes are stirring tropics, right? Okay, the main result that I showed previously, in fact, is published, already published in these two papers. And the first one basically described all features of these Stirring waves and Rossby waves. And also we have the theoretical approach to explain the role of these motion modes in the general circulation. Okay, I guess, bueno, ahora estoy listo para las preguntas. Gracias.
Muchísimas gracias. Bueno, pues ahora tenemos preguntas. Ya podemos
Espero que
ver.
no haya estado tan... pueden preguntar en español, no, las preguntas sí pueden ser en español y las trataré de responder.
Gracias, Víctor. Bueno, pues ahora tenemos preguntas. Alan.
Hola Víctor, ¿me escuchas?
Perfecto, te escucho.
Víctor, gracias por tu presentación. Una consulta, esos Monster Moods que nos has presentado y
Ujú.
que en una gráfica me parece que mostraste que no es está tan fuerte, digamos, no es la máxima presencia de Monster Moods en el Atlántico, digamos, en la parte del Golfo de México donde se presentan los huracanes. No sé si sabrás qué tan asociado está la presencia de esos moisture moods en esa zona con la formación de huracanes, o qué tan relevante es su relación con ello.
Ah, sí. Ya, de hecho, como esto, por ejemplo, representa la actividad de los easterly waves o de las ondas del este. Claro que en el Atlántico se ve más fuerte, pero también tiene muy poca actividad, pero sí sigue estando todavía asociado a las ondas del este en la región del Caribe y México. Y claro que están asociados porque estos ondas del este son los precursores de los huracanes en esta región. Entonces, obviamente, eh, más activos en esta región, donde se forman los TDs y de ahí ya se vuelven huracanes, ¿no? Aquí no estamos plateando obviamente huracanes, estamos plateando los precursores de los huracanes. Y en el Caribe, sí, sí también. Comparado con el resto del dominio ecuatorial, vamos a decir, parecen menos activos, pero todavía muestran mucha actividad y están asociados a la actividad de huracanes en esa región, ¿no? De hecho, tenemos un paper básicamente estudiando ondas del este en el Caribe. Nada más explicando dónde, porque es muy peculiar porque es en la única región donde tú puedes decir, ah, ya, pues, porque toda la teoría que se tiene para explicar esas ondas del este está asociado a la estabilidad baroclínica, pero pues nosotros hemos demostrado que en estabilidad baroclínica realmente no explica nada y lo que explica es lo que nosotros hemos llamado inestabilidad del modo de humedad, ¿no? Que está explicado, de hecho, en el segundo paper que he presentado hoy. Pero en esta región, específicamente en esta región donde me mencionas, el Caribe y el Golfo de México, es en la única región donde las ondas del este todavía tienen características para decir que las ondas del este puede ser explicado como una estabilidad baroclínica, pero no, todavía sigue explicando la teoría que nosotros hemos presentado.
Gracias, Víctor. ¿Alguien más? ¿O Alan puede preguntar, hacer otra pregunta? A ver, Alan, en lo que los
Tengo otra
demás se
pregunta,
alistan.
Víctor, después de que te moleste.
No, no, por favor.
Esa baja concentración, bueno, sí hay presencia de Monster Moods en la parte del Atlántico que mencionabas, pero de alguna manera hay contribución de la cuenca amazónica para...
La cuenca amazónica, sí, pero sí, la cuenca amazónica de hecho es una fuente de humedad. Yo no sé, tal vez a ver, cómo, cómo regresa esta cosa. Ah, ah, bueno, no se puede. Para la cuenca amazónica te quería mostrar la figura esta que no está saliendo, no sé por qué. A ver. Mm. De hecho, la cuenca amazónica representa una fuente de humedad, pero no específicamente para las ondas del este, sino para las ondas de Rossby, que mostré al inicio. ¿Te acuerdas cuando estaba haciendo la separación entre una onda que propaga rápido y una onda que propaga lento? Y presenté Rossby. Y Rossby básicamente tiene una circulación que ayuda a llevar todo o a advectar toda la humedad que tienen, porque el Amazonas es una fuente de humedad bastante fuerte y ayuda a llevar mucha humedad para la región del Caribe. De hecho, y eso pasó cuando nosotros publicamos ondas de Rossby en el hemisferio oeste, porque se creía que no había ondas, ondas de Rossby. Este, están asociados con fuerte lluvia en el Caribe y de hecho los meteorólogos de Puerto Rico dijeron que marca de hecho el inicio del periodo de lluvias en esa región. Y sí, y juega un papel preponderante en la advección de humedad desde el Amazonas para esa región, ¿no?
Gracias, Víctor. ¿Alguien más? Nadie. Vamos a ver si en línea. Pues no tenemos ninguna otra pregunta. Solo yo te voy a preguntar, Víctor,
Ujú.
¿han explorado cómo se relacionan las ondas de calor marinas con estos cambios que han observado en la humedad?
Exactamente marinas no, pero sí estamos explorando los heat waves en la atmósfera y también están asociados a la actividad de esas ondas, porque lo que pasa es que tú vas a tener una oscilación, ¿verdad? Un periodo que tengas mucha humedad y otro periodo que tengas bastante menos humedad. Y entonces, justo en esos periodos, cuando tienes menos humedades que están asociados a periodos frecuentes de heat waves, pero eso sigue siendo en la atmósfera. No hemos explorado todavía el océano, pero sí, en la atmósfera sí podemos tener certeza que el pasaje de esas ondas están asociados a la ocurrencia de heat waves en los trópicos.
Muchas gracias, Víctor. Entonces, Nadia, pues gracias, Víctor. Le damos un aplauso.
Gracias, gracias.
Y bueno, pues ahí te mandaremos tu reconocimiento de participación. Gracias, Víctor.